right, so this is question 3 of the past question 3b. So the question is to suppose that there are 2 goats on an island initially, and the number of goats doubles every year, and 100 goats are put on the island every single year. So how we are to construct a recurrence relation and solve to find the number of goats at the start of the nth year. So let's start by doing the recurrence relation. So from the question, there are 2 goats on an island initially. So how do we write this down with respect to recurrence relation? So we know that is the base case. So the base case is that so let's first suppose. So let's g of n be the number of goats at the beginning of the year. Sorry, at the nth year. Okay, so g of 1, that is the number of goats for the first year initially. So the first year is 2, and they go on to say that the number of goats doubles every year. So now we don't know the next year, so let's say is g of n minus 1. Sorry, so g of 1, that's the base case, is 2, and the recursive case is that, so they are saying we should find for the recurrence relation at the beginning of the nth year. So g of n is equal to, and we are hearing that they told us that the number of goats doubles every year, so it doubles times 2, and 100 are added, so plus 100. So this is the recursive case. It goes on for the other years. So initially there are 2 goats, and for the rest, this is what we use. This is the formula we use. So let me write it formally. So we start with the recursive case first. So 2g of n minus 1 plus 100, and 2. So g of n equals this. For n equals, n is greater than 1, and is 2 for n equals 1. We know that when n is 1, the number of years, when for the first year there are 2 goats there. Okay, so let's go on to solve this recurrence relation. So we'll solve this using back substitution, the iterative method. So how do we do this? Let me write the recursive case. Okay, so this is our recursive case. Now we are going to use back substitution to solve this. So using back substitution, we are going to, so back substitution, how it works is that now we want to get a pattern. So we'll go back 1 year. Since recursive functions, they always reduce till they get to the base case. So that's the logic behind it. We are going back 1 year, 1 year, 1 year till we get a pattern, and we get to the base case, and now we can solve it. So using back substitution, now what are we going to do? We are going to substitute. So let's substitute g of n minus 1 into g of n. So g of n minus 1. So g of n minus 1 is equal to, now we are putting n minus 1 into this formula. You see, it's g of n. Now wherever we see n, we are making it n minus 1. So it will be 2g of, we've seen n, we'll put n minus 1 there, but there's already minus 1 there, so it will be n minus 1 minus 1, that is n minus 2. Okay, plus the 100 here. So we are substituting this into g of n. So that's how it works. So this g of n here, wherever we see g of n minus 1, we are putting it in the formula in g of n. Okay, so g of n is equal to, we are writing this 2. Then g of n minus 1, we won't write g of n, we'll write the formula we had here. So let's make a macro bracket and 2g of n minus 2 plus 100. Let's close our brackets. So all this here is the g of n minus 1, the g of n minus 1 plus 100. So this is how it works. Now let's simplify it. So 2 times 2 will be 2 squared g n minus 2 plus, is a bracket, so this 2 will also multiply the 100. 2 times 100 plus 100. So this is how it's going to look. Now that we've simplified it, we are going to substitute again. So this time we'll substitute g of n minus 2 into this formula. So wherever we see n, we put n minus 2. So g of n minus 2 equals 2 times g of, I said n, we put n minus 2. So n minus 2 minus 1, n minus 3 plus 100. So we are substituting this into our g of n. And g of n now is this. So g of n is equal to, let's write this formula. So 2 squared times what? G of n minus 2. But now we've gotten our g of n minus 2 as this. So let's put our macro bracket there and substitute this wherever we see the g of n minus 2. So we'll get 2g of n minus 3 plus 100. Close your brackets. Now we are done with this side. Let's put the 2 times 100. Let's put the 2 times 100 plus the 100. So okay, now let's simplify. We'll get 2 squared times 2. We get 2 exponents 3. And our g of n minus 3. Then now this 2 squared is also multiplying the 100. So plus 2 squared times our 100 plus 2 times our 100 plus 100. So we are getting a pattern, just that it's not so clear. So let's do a last substitution so that or we can end it here and let's see our pattern. So the pattern here is that, so look at these two in juxtaposition, this, and I think the first one, this. So let's look at these three and see if we can find a pattern. So you can see that this one, it started with 2 exponent 3, reduced to 2 exponent 2, reduced to 2 exponent 1, and reduced to 2 exponent 0. 2 exponent 0 is 1, so we don't write it. So that's the pattern here. Here it was the same. So what we are going to do is that we know that at the kth iteration, what happens? So let's skip to the kth iteration. That's the last one. So we are skipping to g of n is equal to. So before that, let's write a general formula for it. So we can see there is a 2 exponents, a key, a certain number. Then our g is there of n minus, and this is the same as our key here for this one and this one too, for each and every single one. That's what happens. So we'll put our key here plus 2 exponents. This 2 is 1 less than this, so that's k minus 1. Sorry, minus 1. Okay, and multiply it by 100 plus this 2 exponents, what, k minus 2, multiply by 100, so we get to, so it will continue on, so we get to 2 exponent, so 100, so we get to 100. Okay, so this is the general formula, and we know that at the last iteration, that's at the last state, that is the base case. We know that for recursive functions, they end at the base case. So at the base case, we know that g of 1 is 2, and to make it g of 1, we have to equate n minus k with 1. So at the base case, n minus k equals 1, so that we can get this side equal to 1. The g of n minus k, we can get it g of 1. Okay, so what are we going to do next? Now let's make k the subject. So k here is equal to n minus 1. Yeah, so we are making it in terms of n because we introduced the k from somewhere, so we want to make it all in n. So what we do is g of n is equal to 2 exponents n minus 1. That's our k. K is now n minus 1. So 2 exponents n minus 1 times our g of n minus k here is n minus 1. Let's put our brackets, smaller brackets, n minus 1, bigger bracket, plus 2 to the power of k minus 1. K here is n minus 1, so n minus 1 minus 1, that is n minus 2, plus, sorry, times 100, plus, so it goes on till it gets to 100. Okay, and what else? Now we can see that, let's simplify this side. So g of n is equal to 2 to the power of n minus 1, and g of, so n minus, so it's negative, it's basically negative 1 multiplying the bracket, so negative n and negative 1, so plus 1. So n minus n will cancel each other, and now it's left with 1. So g of 1, so that was the point of we equating n minus k to 1, so that we make here the base case. Okay, so g1 plus 2 to the power of n minus 2 times 100 plus 2 to the power of n minus, from here, n minus 3. Yes, so we get to 100, sorry, times 100, so we get to 100.